Let's have a look at the group 7 halogens. Now, on the periodic table, you can find these over, unsurprisingly, in group 7 on the right-hand side, and the group 7 halogens are known as fluorine, chlorine, bromine, iodine, and astatine. Now, that term halogen comes from the Greek for salt formers. Now, this is because when you react a group 7 with another metal element, you often get a salt form. So, for example, if I would take the group 1 metal sodium and react it with the group 7 chlorine, I get sodium chloride. Lithium and fluorine, that would form lithium fluoride, potassium iodide, and so on. So these group 7s, they often form salts. Let's have a look at a reaction. So what we've got here is a gas jar full of chlorine, and we've got some warm sodium going into it, and you can see here it's a really exothermic reaction. It's giving off a lot of heat energy and a lot of light energy. So what's going on chemically? Well, we've got positive sodium ions forming bonds with negative chlorine ions. So this is ionic bonding, and it's going to give rise to sodium chloride molecules. And after this is finished, there's going to be sodium chloride, salt, coating the inside of this gas jar. The trend or pattern here is that the group 7 halogens get more reactive as you go up the group. Now that's the opposite to the group 1 alkali metals, which get more reactive as you go down the group. So the most reactive group 7 element is fluorine, and the least reactive is astatine. Now to understand why this is, let's look at fluorine and astatine. So group 7s have all got 7 electrons in their outer shell, and so they only want one more electron to be stable. They're very close to being stable. This makes all group 7s quite reactive compared to other elements, and it also makes them perfect partners for the group 1s who want to lose just one electron. Now have a look here. In the atom, in the middle of the atom, the nucleus of an atom, we have the positive charge. And that positive charge acts on these negative electrons as they whirl around the outside. So you can see here that this final shell here in fluorine is not far from the positive charge in the middle. These negative electrons are quite strongly attracted into this centre. Now, group 7s want to attract another electron in. And if this final shell is close to the positive, that shouldn't be a problem. It's quite a close, it's not far away, so it'll be quite a strong attraction. This makes fluorine take on an extra electron very easily. Now, look at astatine, this huge one here. Look at the distance between the middle, the positively charged nucleus, and the final shell. To get another electron into this final shell, it's a long way away from that positive nucleus, and that pull at that distance is going to be very weak. So astatine is far less likely to pull in that final electron than it wants to become stable. There's another effect as well, which is called electron shielding. Astatine here, it's got this positive charge trying to pull in another electron in the outer shell, but it's got all these other electrons whirling around between them, between the plus and that final shell. And what these other electrons do is they interfere with this positive charge. They diminish the positive charge because there's all these negatives whirling around in between them. So a combination of distance to the outer shell and electron shielding means in astatine, that positive charge has a much weaker pull on that final electron than it needs to come in. Whereas in fluorine, because it's much closer and there's much less electron shielding, it has a much stronger pull to get that final electron in. And this is why fluorine reacts more readily than all the others. And this is why you get an increasing reaction as you go up the table this time. Okay, here we are. We've got some pictures. We've got fluorine, which is a yellow gas. Chlorine seen here is a yellowy green gas. Bromine is an orangey brown liquid. Iodine is a solid, and we've got some iodine crystals here, and they're a shiny purple colour. And if you warm them up, you get a nice purple vapour. And so as the colours are getting darker as you go down the group, we'd expect astatine to probably be black or not far from black. On this periodic table here, you can see the different states. They're in different colours. So what we've got here in group 7, you can see fluorine and chlorine are in gas form at room temperature. You can see bromine is a liquid, and we've got solid iodine and astatine. It's the only group in the periodic table where we have solids, liquids and gases all represented at room temperature. Now, a common exam question is something like, it tells you the melting points and the boiling points of a substance, and it asks you to state whether it will be a solid, a liquid or a gas at room temperature. Now if we say room temperature is going to be about 20 degrees. Look here, look at fluorine. It's melted at minus 220 degrees C. It's boiled at minus 188 degrees C. So by room temperature, by plus 20 degrees C, It has melted and it has boiled. Now, what state is something in if it's melted and boiled? Well, it's going to be in a gas state, isn't it? So, fluorine is a gas, just like we saw on the periodic table. Chlorine has also melted and boiled by this point. By plus 20 degrees C, it has already boiled. It boiled back down at minus 34, so we know it's a gas as well. What about bromine? It's melted, minus 7, but at 58 degrees C, that's higher than room temperature. So at 20 degrees C, it has not boiled yet. And if something has melted into a liquid, but not boiled into a gas, it must still be in its liquid form. And finally, for iodine, it melts at 114, boils at 183, so it hasn't even melted yet. And if something hasn't even melted yet, then we know that it is in a solid state. Okay, let's have a little look at the colours. As we said before, you've got a yellow going down to green, and then an orangey brown, and then purple, and like I said, we'd expect astatine to be a black colour. Let's have a look at a reaction, a chemical reaction. So we've got potassium plus chlorine. We've got a group 1 metal plus a group 7 halogen. Can you guess what we get? Okay, well, we get potassium chloride. If you're not happy with this sort of thing, guessing what products you get from a reaction, have a look at my video on equations and formula, and that might help clear things up a little bit for you. And it also gives you a little practice on balancing equations. Let's add the symbol equation. That's the word equation, and this is the symbol equation. Now, it's important that you realise that the group 7 halogens go round in pairs. They're diatomic. Okay, so they're diatomic, so they always go around in pairs. Cl2, F2, I2. Okay, if you don't get that right, then you won't be able to balance it properly. So if you want some practice balancing equations, pause the video now, have a little go, and then unpause the video. Okay, so if you've had a little go at that, this is how you should see it balanced. 2 potassium atoms with a chlorine molecule and 2 molecules of potassium chloride, and that's balanced now. Okay, lastly, I want to talk about the group 7 displacement reactions. Now, what's a displacement reaction? A displacement reaction occurs when one atom or molecule steals from another. So here we've got chlorine plus sodium bromide. Now, chlorine is a group 7, bromine is a group 7, and bromine's got hold of this sodium, this group 1 at the moment. Now, you can see here that chlorine is more reactive than bromine, and that means it's stronger. That means it has the ability to steal from it. What's it going to steal? It's going to steal this sodium. Chlorine steals the sodium, and we end up with sodium chloride, and poor old bromine gets all left on its own there. So that's a displacement reaction. A higher up group 7 halogen will steal from a lower down group 7 halogen. And here's the symbol equation just down below. Remember, diatomic, and that helps you balance it. Here's another one. What would you make of that? Iodine and potassium chloride. What would we get? Well, here's iodine, and here's chlorine. Which is stronger? Which is higher up on the reactivity series of group 7s? Chlorine is stronger. Now, chlorine's already got hold of this potassium. Can iodine steal from chlorine? No, it can't, because iodine is lower down on the reactivity. So, what we get here is no reaction at all. Okay, so we've got, if they're higher up, they can steal from the other one. If they're lower down, they can't. So fluorine can steal from any of them, and astatine can't steal from any of them. Okay, so that's called a displacement reaction. And that's it really. That was a very, very quick run through of the group 7 halogens. Thanks for watching.